People next door. Patrick Conrad, whose PhD thesis comprised of the initial part of this work, and Yusuf was his advisor, and Yusuf and I have been talking for a few years now, and Aaron Smith is a collaborator who graduated from Stanford and now is a professor at Ottawa. So the focus of the talk is the following. So I'm going to focus on computationally intensive problems. So I know that there's a huge background of the audience, like diversity in the background of the audience. So I'm going to make it very introductory as much as possible, I promise, so that even if you've not seen some of these ideas, you'll get something out of it. That's the way I've planned it. And then I'll show you the connections. This is a big data talk, and this stuff is directly relevant to Bayesian inference in large data sets as well, but that's not necessarily so the methods I'm going to talk about is quite general, but they're applicable in this particular context as well. So the theme is that the Bayesian inference in these problems proceeds via Markov chain Monte Carlo methods called MCMC. I'll explain to you a very specific algorithm. And then it turns out that in these problems, it's really difficult to design them because they take a really long time to run. So what I'm going to talk about is how to think about approximate MCMC algorithms to make it feasible for them to be running in a reasonable time and get a valid answer, statistically speaking, and also do some mathematics behind it. So the outline of the talk is going to be I'm going to start with a motivating example from computer experiments, and then after setting up the basic notation, I'll explain the key connection between large data sets and what we're trying to do here. And then I'll give you a brief review of what people have done before so far, and then I'll explain our algorithms and then conclude with examples. Feel free to stop me with questions at any time, please. So the motivating example is the following. So the ice sheet in Antarctica is melting. So on the left, this problem came from some climate scientists at MIT. And on the left is, I don't think you can see here, there's something called Pine Island. And I think it's about here. I don't think you can see it here. It's like this. And that's a magnified view of that. So the point is that the ice sheet is melting. And the question they wanted to know are the following. Like, for instance, how readily is heat absorbed by the ice? How much mixing occurs at the ice-ocean interface? And, like, can you really have... So basically, to answer many of these questions, they have physical models for answering many of these questions. So, for instance, one of them look like this, so don't be worried. I don't understand any of this. I just understand what the basic equations are. And so what they're interested in this, for instance, in this particular problem, for instance, they want to know the viscosity at various temperatures and all of that, among other things. And what of course, they collect data at various points, let's say, from around this region. And they have physical models for it, and for instance, like this. And what they want to know is what is, for instance, a viscosity, among other things. So it's a very simplified problem. So now, from a statistical point of view, this is an extremely well-studied problem. Like, if you know the data, so this is called the forward model. If you knew the viscosity, and then we know how to solve these equations. And then we have collect data from it, so that'll give you a simple likelihood model, and then the statistical paradigm at least tells you how to get the uncertainty for the viscosity parameter. The difficulty with this, and this is the key problem, is that this stuff is extremely hard to run, in the sense that actually people take PhD theses and multiple PhD theses to actually fine-tune these algorithms. For every single run of this, actually, for instance, takes 2 hours on a supercomputer. Right? I mean, that's just like being generous. So that's the problem. Now, so in the last 10 years or so, especially, like, engineers have really gotten into statistical inference of these problems, and there's a huge revolution going on called data assimilation. And the point is, they call studying It's the engineering version of data science, so to speak, that they have these physical problems and they have data and they want to understand and do inference. Right. So let me set up the problem and then I'll come back to the big data problem in a minute. So this is, so typically, so in the example I showed you, let's take d is equal to 1, and so you're just interested in the viscosity parameter, and you have typically prior information. So that's the probability density. And the likelihood function is where, so d is the data, and f is this, I'm going to consider f to be this black box function, which is the forward model I showed you, which is basically the the underlying PD model. And imagine that the measurement errors is Gaussian, and there are natural reasons to consider why that's the case. So given data and one run of the PD, you know how to compute the likelihood function, which is just basically evaluate the function with the Gaussian errors. That's your likelihood function. So, and once you have that, it's, you have a probability density pi theta, which is the posterior uncertainty from your data set, which you just saw. So this is the problem. And the goal is basically to get either visualize what this guy looks like and get samples from it, compute its mean, uncertainty, etc. So again, the key difficulty is that, okay, so this is not big data yet, right? So this is one-dimensional parameter. It's just that to run this is extremely hard because of this computing this guy, which is really a black box, and some underlying supercomputers doing something, and we have no control over it. Now, this is the, let me continue with the introduction and tell you how this is actually done. And if people have not seen this before, let me show you a very, very simple algorithm to visualize, to get samples from pi theta. So this is the idea. So the idea is the following. I didn't see anybody use Blackboard, so I decided to break that trend, and hopefully people will follow suit. So you have a probability density pi of theta. This is in one dimension, let's say, like this. And so what I'm going to talk about is, so the idea is to get samples from it, and the revolution that happened about 20 years ago in Bayesian statistics, which I study, is that you can use computers to construct a Markov chain, to set up a reversible Markov chain to get samples from this density. And the easiest one is the following. So the key the point is the following. So this is of the form, this black box function L theta, this is proportional to this times P of theta. This is your prior distribution, and this is your likelihood function, which is coming from this black box device. And you don't, so this will be a probability density if you take this to be, this is equal to the 1 over z, L of theta, pi of theta, p of theta, but this is the normalizing constant, and if you're from statistical physics, this is the partition function, so to speak, which is this integral of this over the entire parameter space. So I'm going to set up a Markov chain that will sample, whose stationary distribution will be this density, so that you can run the Markov chain long enough and report samples. And the beauty of this is that the algorithm I'm going to describe doesn't need to know what this constant is. Okay? And that's why this is still hugely popular. The idea is the following. So this is my cartoon for the state space. If you assume parameter theta is an RD, in this case d is 1. And you start from a point. This is your initial point x0. And you randomly look around anywhere. Okay? And then you go to that point with certain probability, and you stay where you are with certain other probability. And I'm going to tweak these probabilities to be in such a way that the chain is reversible and whose stationary distribution is what we want. So that's the idea. And this is, you can think of this as a random walk algorithm. Basically, you're doing a random walk on the state space measured by the stationary density. And the probability you'd go to is the following. So it's a minimum. If theta is your current point and theta 1 is your new point, the probability you go to is the minimum of 1 and pi of theta 1 over pi of theta. Okay, so you can see that, right? So if the new point is in such a way that the pi of theta 1 is greater than pi of theta, then this number is greater than 1, so you always go. But the new point is such a way that if pi of theta 1 is smaller than pi of theta, then you'll go with certain probability. and you stay with certain other probability. That's it, right? And the beauty and the reason why you don't need to know the normalizing constant, which some problems is really hard to compute, is that the normalizing constant vanishes from this ratio. That's the idea. So this is called the random walk Metropolis algorithm. It started with roots in, during the war. I think John von Neumann and other people started this, and huge history. So this is the simplest algorithm you can think of, right? So, and and you can think of this as the stochastic version of gradient descent, random walk, hill climbing, whatever you call, whatever way you're comfortable with thinking about it. Okay, so that's setting up the problem. So this is your prior distribution, which is p of theta here, and the posterior distribution is in the green curve, which is the pi of theta. And they could be completely different because the data would actually tell you something different from what we know about the parameter. And this is my cartoon of how the algorithm goes, the random walk goes, that you start from here and then accept, etc., reject, and then keep going, and then explore the entire contours. Okay, so questions so far? So this is the way, if this L function were easy to compute, this is where this would run, and this will run in less than a minute, for instance, and you get 100,000 samples. Like we have very, very efficient versions of this. So the challenge here is that if this is really hard to compute, how do you really make this work? And here is the formalization of that, what I just wrote on the blackboard. So the goal is to construct a reversible Markov chain whose stationary density is pi. The way you do that is, my theta 1 here is qt. So you go from, so you can think of q as the normal kernel. So you're basically doing a random walk. And this is the acceptance probability of the minimum of the pi evaluated at the new point, and the ratio of pi evaluated at the new point and the pi evaluated at the old point. This is setting up. As you see, if you want to take 100,000 samples of this, which is not large by any means, because the price to pay here is that you don't get independent samples. The Markov chain is correlated. So of course you need to let it run for a while and then report samples. So that it is properly mixed, etc. So you see, for every evaluation of this, for every point that you want the algorithm to run, you want to evaluate this L function, which is really hard, right? This is the challenge. Now here's a connection to the big data stuff, which is a very simple instance, and this is a real problem that I'm dealing with. So imagine that, here is another instance where L is hard to compute. So you have the pi again, theta is one-dimensional, and you have p of theta is the prior distribution. And imagine that you have the likelihood is IID data. This is the simplest one you can think of, but you have a lot of them, right? And so in that case, the likelihood is a product of, or if you take the log likelihood, it's a sum of n terms. Of an easy to compute function, but you still have n computations to do, and n could be really large. And there are and the same problem happens because even though this algorithm is extremely simple, it's hard to run. Each step takes a lot of computational time. So you see, and there are many other real versions of the problem where the algorithm is hard to run, especially because of the fact that you have a large data set and you cannot compute the likelihood function easily. So that's so what do we know about, so engineers have studied this before we started working on it, and the main contributions were as follows. Let me summarize in 2 slides what they did. So what they do is they want to construct an approximation for this L function that we cannot compute. So what they do is they pre-compute the L function on a grid before, and then they stop. And then the rest of if you want to evaluate the L function in any other points, they approximate using some polynomial methods or some Fourier expansion, etc. So the point is that to compute the truth only on pre-specified points. and this is a classic paper in statistics. This and this, both are statisticians. But like these people considered constructing the grid over the prior distribution, and as I told you before, the p theta could be completely different from pi theta. So you want to, even if you want to approximate the L function, you want to approximate L where this guy's concentrates. So there are people later on, Yusuf in 2014, before we started working on it, had methods in which you can approximate the function where the posterior distribution is concentrated. Okay, but what is the problem here? So the problem, approximations, I believe in approximations, actually I think in approximations in some way. The difficulty here is that there are two kinds of approximations going on, so to speak. So this uncertainty comes from the sampling algorithm because you have an underlying stochastic thing which is sampling from a state space, from a probability density. And that will cause uncertainty, that will inflate that uncertainty that you're trying to estimate. The other thing is the uncertainty and the approximation error coming from the fact that you are approximating the L function most of the time. And so until then, before our work, the key challenge in this field was that how do you don't have control over these two. Like there is an uncertainty due to the approximation error, and there's the uncertainty due to the sampling error. And you can approximate arbitrarily well, people would say, that was the argument, but then the other argument was that you don't know what the sampling algorithm usually does, so you don't know how far you have to approximate a priori. That was the challenge. So here's our idea, and I think there's much more work to be done in many settings, especially in large data sets. I think this is an important thing to thinking about. So the idea is to do asymptotically exact approximation in the sense that we're also going to do approximations of the L function, but in such a way that asymptotically that error vanishes. Asymptotically in the algorithm, like when you take a large number of steps in the algorithms, the approximation error vanishes. So the point is to balance simultaneously the uncertainty due to the approximation and the uncertainty due to the sampling error. There's some key connection with before there was one paper that's very relevant to us by Kristen and Fox. But they still needed to run the model n different times. And our goal is not to run the model, the true model, a lot of times. Our goal is to minimize the amount of time you actually run the true model, but still make it work. Okay, so this is the slide I showed you before, which is that you have the acceptance probability, the L function, and this is the Markov chain. And in the naive version of the algorithm, you have to evaluate L n times if you want n samples. Our method is the following. So at t here, for instance, is the algorithmic time t. I'm going to continuously approximate function f as the algorithm runs. And the goal is to approximate it finer and finer as the algorithm runs so that the function L or f is the black box function, L is the likelihood, but if you approximate L, you approximate f and vice versa. The goal is to approximate it finer and finer so that it actually converges to the truth. And the approximation is built on the points where you actually evaluate the function f on the true number of evaluations on f. The goal is also to minimize the number of true evaluations, okay? Great. So one caveat is that you cannot hope to have, especially if the parameter set is large, you cannot have to have a global approximation because the cost of computing the approximation based on global approximations like basis functions or Gaussian process, etc., will go prohibitively large as a function of the dimension because you need to have all of the points that you've computed to approximate a function at a local point. And often that's not even necessary. Okay, so our algorithm uses 3 key principles from statistics, and this is worth discussing on its own. One is that it uses the idea of local approximations, and the engineers love this because they always like the derivative-free approximations. And this is something that statisticians also have worked on from the early 80s, and it's worth going through those methods in retrospect and see what we can say about these problems. The second is something called cross-validation, which most machine learners know what that is. And the third one I'm really excited about is the idea of experimental design. And design is something, again, the statisticians have really thought about very hard, and I think it's personally exciting for me to use some of those principles for designing algorithms in this large data set context to maximize efficiency, so to speak. So the first idea is the following. So the local approximations, I've already told you what this is. Basically, that instead of approximating the function globally, you actually use the points. So if you have a function here, this is the point you want to evaluate the function is. You only roughly take the points around it and not globally, and construct an easy approximation. And this lowest regression basically does this. And there are many other methods. I just chose one. And it's easy to write. It's easy to write an R code. Like there are packages which does it for us. The point is, this radius R is roughly as a function of dimension should be order d squared. So basically, the point is that if you want to evaluate the function, here, you just go a radius of about order d squared and find you go for a radius so that you find about d squared points to do the approximation. And the theory tells us that if you do that, then you have the function and its local approximation have this bounds as a function of the radius. Not only that, while doing this, you also have bounds on the derivatives of f, surprisingly. And this is easy to compute. So that's the first ingredient. The second ingredient, so it turns out that initially, if you don't have many points, the radius in which you have to go is quite far. But as and when you get more points, the radius shrinks to find order d squared points. So the second idea is cross-validation. And this is also very interesting. So remember, if the goal is to have the approximation error 0 at infinity, you cannot escape from the fact that you have to evaluate the true model infinitely many times, because there's no way the approximation error will go to 0 if you don't evaluate the model infinitely many times. But the point here is that the fraction, so if you want n steps from the algorithm, the observation here is that you only need to evaluate the true model a fraction of that time to still have the approximation error go to 0. So for instance, it turns out that, and we'll see in examples, I can do this and have a reasonable answer with only 10% of the time. So the idea of cross-validation is the following. So at every step of the algorithm, I randomly toss a coin and evaluate the true function with beta t probability. And if beta t sum up to infinity, then we know from Borel-Cantelli, for instance, that you have evaluation of the true model infinitely many times. So I randomly toss a coin, let's say with very small probability, and decide to evaluate a true model. And most of the other times, I decide to approximate the function. But the cross-validation is what it's saying is the following. So imagine that this is the point you want to evaluate the function at, and these are the points you're going to use for approximation. I want to see how well any particular point is overly influencing the approximation. So what I'm trying to do is construct the approximation by using all the other points, leaving one point at a time. And I can roughly see how the average and what are the outliers, etc. And in particular, if one point, if all the other approximations are working okay, as compared to one point which makes the approximation error really high, then I think the approximation is really poor and decide to evaluate a new point. Right? So in summary, what I'm trying to say is the following. So I cannot escape the fact that the model has to be evaluated many times, infinitely often, but I can get away with the fact that because of Borel-Quintelli, I can only evaluate the true function. I need only evaluate the true function only a fraction of times. But I also want to keep in track of how the approximation itself is doing. So I don't want any particular point to be overly influencing the approximation. So cross-validation helps you counter that. Yes?
So you do these local approximations.
Yes.
So you have lots of local approximations.
Yes.
And are you expecting that they're all coming from the same fundamental model?
Yes.
And so how are you going to put them all together when an alternative might have been, okay, this part of the space, this is the model with some parameters.
Yeah, so that's the beauty of local approximations, that it tailors to exactly that. Like if I were to do this globally, I will not have the flexibility to do that, exactly that, what you're saying. Yeah. Yes. No. So the point of the crosses is to actually evaluate the function fully. Yes. Okay. And the last one is, when you decide to evaluate a point, where do you evaluate it? So typically you would think where the algorithm tells you to go. But this is where the third principle of statistics, the design, comes in, which is that imagine that the algorithm tells you to go here, okay, and typically you would think, okay, let's evaluate the true function here. But if this is the case, let's say, in this case, you can. My point with this slide is that there are these are two fundamentally different instances. For instance, if you approximate a function here, then that approximation is predominantly coming from, and this is your radius, so that approximation is predominantly coming from the points in this direction, and there is no points in this direction. Right? So naturally, and depending on how the geometry of the set is and how the function behaves, you want to find an approximation. For every approximation, you want to find points which some sense geometrically are filling. So in order to, and there's a way to construct points where you evaluate the new point using natural loss functions and the maxim designs, etc., which basically tells you how to construct a space-filling design in any point so as to approximate reasonably well. And again, there are, for instance, R packages to do this for us. So let me summarize. So the idea was to find local approximations and reduce the model evaluations, and it needed key principles. 3 key principles from statistics. One is the local approximations. The second one is that evaluate the true model less frequently and use cross-validation to keep a check on how the approximation is doing. And the third is the design, which tells you where to evaluate the new point. So the theory I have is modest, but it still shows that, for instance, if the parameter space is compact, then the Markov chain, this approximate Markov chain, converges to the true distribution asymptotically in total variation. It's quite a strong norm, but it's a natural norm in Markov for talking about convergence of Markov chains. So basically, this result tells us like what we want, that the model asymptotically gets rid of the approximation error. In the interest of time, I'm going to get rid of the proof steps. When the parameter space is not compact, you need some extra conditions on the target density. For instance, that it has some tail conditions like Gaussians, or some other conditions that you need. And this is really, this is also one of the instances where the theory gives insights about the algorithm. It turns out that so here is one mathematical fact which is interesting. So the way the Markov chain works, the reason why they have the stationary distribution as pi typically is that if you are far out in the state space, there needs to be some mechanism that pulls you towards the center of the state space. And typically this is some drift towards the center of the state space. It turns out that if you have approximate algorithms, if it turns out that if it has heavier tails, the approximation algorithms can mess with the tail so that that property is destroyed. And the inherent mechanism present in most of these chains to come back to the center of the state space can be disturbed so that this isn't ergodic anymore. So what these conditions are saying is some mechanism to make sure that this wave to coming back to the center of the state space is still preserved while you're messing with the approximations. Sorry? So K true is the underlying. Imagine if you could do this run exactly, right? Like there's an original algorithm. If you could evaluate the function easily, then you would run an algorithm. Of course, that need not work, right? So I'm saying if that algorithm works, like what people were using before works, then our thing also works. That's what I mean. Thanks for the question. Yeah, it's very modest. So all I'm saying here is that if you have a thing that works when you know how to compute L properly, I can give you a device to make that work when you approximate L. Yeah. Yes, so the convergence, yeah, so it turns out that it's not that bad, fortunately. So the mixing times, I can talk offline, but the mixing times are roughly the same. And let's look at the numerics and you can just see. Okay, so I'm going to take in the numerics I'm going to show you a simple forward model, and I'm going to do the approximations with Gaussian process regression or lower order polynomials, the lowest regression I talk about, and the algorithm that I'm going to talk about, the K-true, is a simple random walk, which is this one. But although I discussed it with a very simple algorithm, all of this goes through in various fancy versions of the algorithm. So you can see this is the relative error with respect to the number of steps of the algorithm. And not surprisingly, all of these, so this is evaluating the true model, running the true model, and these are the other approximations. One is a linear, quadratic, and a Gaussian process approximation. You can see as the number of algorithm steps increases, the approximation, the error goes down, which is not surprising. What is interesting is the following. If you look at the true number of model evaluations as a function of the algorithm, you can see that our approximation algorithms only use a fraction of the true number of evaluations. And this is what we wanted to do anyway to start with. Here's a problem on an elliptic PDE as a forward model, and you can really see that this is the true algorithm, which uses about 10,000 iterations, versus our approximations, which only use about, 500 of them. I have 5 minutes, so let me show you another example. So we did this in the ice sheet model, and this was the posterior distribution. And you can really see that it has some non-Gaussian features, and also they're not necessarily well behaved. Like some of them have really some concentration relative to the other parameters. So it's not a trivial model. And if you did this naive one, for a single run of the algorithm would take about 2 months for this to get an answer. Ours runs in about a day. So let me. So one of the questions that asked. So what are the possible pitfalls? The pitfalls. The method is, okay, how does it interact with this? So there's a beast that's doing all the work for us, which is this underlying Markov chain. And what we're doing is messing with the approximation and therefore inherently messing with the mixing properties of the underlying Markov chain. And it is also, because we're using approximations based on past data, the chain itself is not Markovian anymore. It uses information from the past. So it involves new mathematical challenges, and it's interesting to study them and to get the convergence properties of that. And in general, it turns out that even though it has some problems, it's manageable. Like, you have some control over what the approximation errors are, what the mixing times are, and you can quantify many of that. So, I worked out what the implications for the large data sets as well. Some of the same problems come in. But in general, I have a Biasvariance trade-off argument that would tell you, if you have a large data sets and you're doing this approximation for running this Markov chain, like, what is the price you have to pay in terms of the asymptotic variance and the asymptotic bias, and also in terms of the computational budget you have. But there's much more work to be done here. And there's much more ongoing work. So in summary, what I've done is the following. Okay, so why does any of this work? All of this works because of this inherent assumption that this underlying function L is smooth. Therefore, to know the value of it reasonably well, you only need to know the value of it is in nearby points, and approximation methods tell you how to do that. Once you can find approximations, you can put that into the existing machinery and make the stuff on the MCMC work. And it also turns out to be robust to various algorithmic variations. Like, a lot of people use different software packages to fit these, but our methods seem to be universally applicable to all of those. And these are, for the experts, that are so much more one can do in way of approximating using sophisticated MCMC methods, and it'll be interesting to work out the implications of this idea in those problems. And there are 2 papers and a few more coming. So this is the one I wrote with Aaron Smith a while ago about having the Biasvariance trade-off argument for this problem. And this is the first paper with Yusuf and his team that we published in JASA, which lays out the skeleton of what this method is. Thanks very much. Yeah.
So you said that the result you get asymptotic, or you get ergodicity, but you also mentioned asymptotic bias.
Yeah, so there are 2 things. So in the problem I mentioned to you, you have ergodicity. That's different. But if you, in general, the people have worked out that if you use this kind of thing that we're doing, which uses past data to construct the future trajectories of Markov chain, you will have asymptotic bias if you're not careful about that. And in the large data settings, you do really have that.
Because you haven't gotten to infinity.
Yes. And that in that setting, it's not necessarily even optimal to think about a perfect approximation, right? Because unbiasedness might give you more variance versus a little bit of bias reduces variance. So that's why the Biasvariance trade-off argument comes in. Yeah, question?
So I just want to check I understand you correctly. With the local approximations, when you mentioned that it's scaling with order of e squared, so that's scaling the number of points that you need to make a good local approximation, is scaling with the dimensionality squared.
Correct.
And that gives you a good enough approximation.
Correct. That's what the theory from the derivative-free optimization literature tells us. So we directly use that.
And it also depends on how far away you're having to look. So
Yes. So we don't have a control over that.
yeah.
But and the picture I showed you is that it turns out that that radius shrinks as and when you get more points.
That makes sense. Thanks.
Thanks again.